In this video, we are gonna talk about partial reconfiguration using the Vivado project flow. For this goal, we create a new project, file new, project new. Next, we should have a name and address for our project file. We use the RTL project. Here we can add our sources for our project. Each partial reconfiguration project should have at least two parts. First, the static part, which here is a light gray. Uh, this static part is always the same in the art design, but the dynamic part, which is a dark gray here, uh, could be changed dynamically when system is running and the static part are doing its job, but the dynamic part could be changed. And we should have some RMs, reconfigurable modules, for each reconfigurable partition. Our dynamic part can consist different reconfigurable partition. Here we have just one reconfigurable partition and some reconfigurable modules for that partition. Okay, we will add here our static part, which is just a top VHDL. It could be different sources and different IPs, but we just have one file here. And we will add one RM per reconfigurable partition. We just have one reconfigurable partition, and here we can add just one reconfigurable module for that partition. Okay, our reconfigurable module here is just a full adder. It's not a big design. Next. Here we can add our constraint file for the static part. I have a zibomaster.xdc, which is my constraint for static part of my design. Next. Here I can choose a board. I use Zibo board. And finish. Okay, our project is created right now, and we have a static part and one reconfigurable partition, which is our dynamic part. Right now, we can migrate our project to reconfigurable partition project with clicking on Tools, Enable Partial Reconfiguration. This action is not reversible, so if you need to have your flat design, you should have a backup from this point. I click on Convert and it cannot be reversed anymore. Okay, after enabling partial reconfiguration, we will have a partial reconfiguration result here and a configuration window here. For each reconfigurable partition, we should right-click on the source files in the source 1RM, which we already added for that partition. Right-click and create partition definition. We should choose a name for a reconfigurable partition. I use RP. And we should have a name for reconfigure module, which we already added. After defining a partition, this icon will be changed. Okay, if we have more reconfigure partition, we should do these things for all of them, but right now we have just one. For next step, we will click on partial reconfiguration result. Next. Here we should add all of our RMs in our design. I add RM2. Okay. Here I just add the RTL file, but if we add a netlist, we should click on sources are already synthesized, and we should declare the top module here. I don't need that do that because I have a RTL file, but I need to assign a name, a unique name, RM2, and okay. If I have more reconfigure module, I should add them, and I should be careful about partition definition name. Here I just have one, but if you have more, you should be careful about that. Okay, right now I create automatically some configuration. The minimum number of configuration for uh, implementing all our RMs will be created automatically, and we can change these, but I don't need to change any of them. Next, here we can add reconfigure runs. I use automatic option. Okay, here we will have one parent implementation. Our static part of design will be use the implementation one, and each child will use static part from his parent and implement one RM. For example, this use the static part from implementation one and implement the partial reconfiguration for RM2 and finish. Here we add a necessary part for partial reconfiguration, and we can synthesize the design, but there is some point which I should like to mention here. First, if you have any IP in your reconfigure modules, you can add it right now. You can add one IP for one RM. If you need to use, for example, a FIFO in two or more of your reconfigure modules, you should duplicate that IP, and you cannot use the same IP more than once. I don't need any IP here, so and you can when you add your IP, you can right click on your IP and choose the RM, but right now we don't have any IP. Right now I can synthesize the design. It will take about a few minutes, or even for a big design, some hours, so I pause the video. Okay, the synthesis is finished, but we can run implementation. But if we do that, we will have an error showing that we didn't declare a p block for our partition. When we declare any partition, we should draw a p block for them. So I open our synthesized design. Okay. Uh, we have a U1 here, which we should draw a P block. This is our reconfigure partition, and we should draw a P block. I'll right click on that, floor planning, and draw P block. Actually, floor planning is not an easy thing to do. We should be very careful about different parameters and a method of hierarchical design, and it is an iterative work to do, and we should do it over, get feedback, and do it again to gain performance. But right now we just talk about the points which is important for partial reconfiguration, and obviously if you need a performance you should be careful about your partial reconfiguration. There is very good resource about that in the Xilinx website and on the YouTube. Okay, I just drew a small P block here, and I will right click on that and go to the P block properties. Here we can see the resource which you use. Our P block have, for example, 48 slice of LUTs, and we just need 2, and it is 4% utilized. But be careful, because you should draw a P block which have a superset of your RMs. For example, if you have one RMs which need 100 lookup tables and 100 register, and you have another RM which need a 500 LUT and just 2 register, for example. It is not a logical relation, but maybe it is. And you should have 100, at least 100 register and 500 lookup table. You cannot have less. It is a reasonable work to draw a P block for your biggest RM, but you should be careful, because maybe you have a small RMs, but it have a P block, but you don't have a P block RAM, and you don't have a P block RAM in your big RM. It should be a superset of your resources. Here we don't have any violation. If you have any violation, it will be marked with a red line, with red color. We go to the properties. I will activate the reset after reconfiguration, because after my reconfiguration it will reset my dynamic part. So my dynamic design will not start from uninitialized state and a random state, and it is very recommended by Xilinx and very good feature of very recommended to do in the 7 series, not ultra scale. And we have a snapping mode. I will put it on the loading, because it is could be off, on, and underloading. If it is off, your P block should be drawn manually very carefully. But if you put it on the on or loading, the Vivado will automatically resize your P block to meet the constraints of your design. For example, if you have you active the reset after the configuration, your P block size should be as tall as your clock region, and if it is shorter than your clock region, it will not be possible to active this feature. But with activating snapping mode, the Vivado automatically will change your P block size and to meet your constraints. Another important things to be careful is that you don't need to draw your P block in the resources which are not reconfigurable, because it will produce some errors, and the edge of your P block should not be between 2 interconnect column. So If you are not worried about these kind of things, just click active snapping mode and you are good to go. The difference between loading and on, you can use on and you can use loading. I use loading. Is that if you put on loading, if there is any trade-off between loading and place, uh, the area of your P block, the snapping mode will go for a loading. For example, if you choose your P block edge on the vertical edge on the between two interconnect, uh, the loading mode will not change it, but uh, it prohibits the placer to place the CLBs in the next to the edge, and it will be very good for loading because that part could be used for loading but could not be used for placement, and it is very good for loading. I will use loading and you can use loading or on, depends on your project. Okay, I guess we are good to go. I will run implementation. I will save the constraint generated by the floor planning. I will use a new file because I don't want to, that constraint will be added to my constraint file, so I just use a okay, it takes a few minutes or a few days in a big design, so I pause the video. Okay, the system is implemented right now. Finish and generate bit stream. Okay, after the generating bit stream, we open target device. We program a design. We will use the implementation one top bit, which is the configuration for implementation one, the static part, program. Okay, we have our configuration one, which is a full adder. If we want to change our reconfiguration, we can go to the program. Right now, we just use a partial reconfiguration for RM1 and program. With this action, our device is partially reconfigured and we have our full adder working. We should go to the implementation one, and we go to his child implementation, child 0 from implementation 1, and we have our next reconfigure module RM2. Okay, right now our FPGA are configured for RM and which is RM2, which is a full adder with a NOT in its output. Okay, we are done. I maybe I upload another video. It is a partial reconfiguration, but we use a reconfiguration with Vivado. And if we want to trigger the reconfiguration using uh, our hardware design or a processor like ARM or microBlaze, we should have an IP in our design which manage the reconfiguration. We will talk about that in next video. Good luck.